Unlike search algorithms such as depth first search and breadth first search, tracing the progress of search algorithms like simulated annealing, these optimization-based search algorithms is not straightforward. Mainly because they don't focus on the path, but they focus on the end configuration, the solution that we are looking for. So tracing these algorithms, that is seeing how they progress over iterations, is very difficult. But actually to get deeper insights into how the algorithms work, how such algorithms evolve their parameters over time. For example, in the simulated annealing algorithm, how temperature scheduling changes the overall objective value or the probability within the calculations. And all of those are very important for us to understand and see how these things change over time. So in this video, what I am trying to do is illustrate the progression of those variables by trying to apply the simulated annealing algorithm to a very tiny problem of designing a single neuron that takes two Boolean variables as input and acts as the Boolean AND gate. So what we want to do is find the optimal values of the weights for the first input X, the weights for the second input Y, and the weight for the bias, so that these optimal values of the weights make this overall artificial neuron serve as a Boolean AND gate. Here, let's say we have, we're designing a small neural, one neuron, artificial neuron, that takes in as input x1, x2, and a constant value as input, and has three weights. And what we would like to do is build this neuron to serve as a logical Boolean logical AND gate. So in other words, whenever x and let's say this is y, x and y are both equal to 0, the output should be a 0. When both are 1, the output should be a 1. And when both are different, then the output should be again a 0. So what we would like to do is frame this problem as an optimization problem where we want to find the optimal values of weight b, weight x, and weight y, starting with some random values such that once the weights are all correct, then the inputs, sort of whenever there are inputs, zeros and ones and so on, the entire function that we have serves as a Boolean AND gate. And in this video, what I would like to do is trace the simulated annealing algorithm at least for a few loops, one or two loops, so that we get the idea of how configuration changes, how temperature scheduling works, how delta E is calculated, and all of the nuances in this algorithm. So what I have here is in this column, so here I have iterations, and in this column I have initial current configuration. Let's say we start Wx, Wy, and Wb, the three weights, as 0, 0, 0. And then let's say these are the next random weights that we can generate, or the next possible state that we could go from the current state. And for the next configuration, what I've simply done is taken the current configuration and then added a random number between -2 and +2 to it, so we get the next random sort of Wx. Similarly, I have next random Wy and Wb. So these three numbers, simply take these three numbers as input, add -2 to +2 randomly, and then generate new set of next configurations. And then I have a temperature schedule here. My temperature schedule is starts with 1, and then is the next temperature step is the current temperature step divided by 1.2. So T next in my setting is T current divided by 1.2. So this gradually monotonically decreases the temperature over iterations. And then before I get into delta E and P, let's look at these. So here what I'm calculating is the actual AND computation. So take my current value of Wx, current value of Wy, and current value of Wb, the three biases. And then when X is 0 and Y is 0, calculate the output. So this gives me the value of the function when X is 0 and Y is 0. And then this is simply the sigmoid of my input, and then expected output 0 minus the actual output that I'm getting from the function, and calculating the difference between the two and absolute of it sort of gives me the error that the model is currently making for the input configuration x equals to 0 and y equals to 0. The model should be correct here. That is, the error ideally should be as close as possible to 0. Similarly, the output of the function currently with wx equals 0 and wy, wb all equal to 0 is also 0.5 for the case when x is 0 and y is 1. So here we multiply 0 times wx, 1 times wy, and then 1 times wb. So this again gives me the error for this case when x equals 0 and y equals 1. Similarly, we calculate errors for all the remaining two cases. So then at the end, what we have here is the sum of all the errors. So in other words, I could say that this is the objective function or the value total that we are trying to minimize for this problem. So if I change wx, wy, and wb to certain other values, the total error for the objective function will change, right? So say if I increase this to maybe 1, the overall sum might change. Say if I change this to 3, then we notice it went up to 2.9 and so on. So if I change the weights, then the output also changes, the objective value also changes. So now that we have the value of the objective function, that is the value, we can calculate also delta E. Now here I've calculated delta E, and according to the algorithm, delta E, or change in energy, is simply the current value of the objective function minus the future value. But here we are yet to calculate future value, because in order to calculate my E next, or the subsequent value of delta E, I have to have the next configuration ready. So say this, as I said, this is the original configuration. So the random next configuration, let's say, is 2 to 1. So let me start from here. Let me copy it, and I'm going to paste values here. Paste special values only. So now this is, please ignore the changes here, because Google Sheets automatically updates the random values each time. So even though we don't see 2 to 1 over here, that is what it was and that I'm copying. So it doesn't matter that this value change as long as we have one next configuration for us. So now we have this 2 to 1 as our next configuration. And so going back, if I continue this this row, I see that now the objective value, objective function's value is 2.64, which is worse than the current objective value that we have. So let's go back, and what we want to do is calculate delta E, that is change in energy. In other words, we want to see E current, which is 2.0, minus E next, 2.64. So E current minus E next will be minus 0.64. Now this is a negative energy. In other words, we have made a bad move. Our configuration change is worse than what it was before. Now, according to the algorithm, whenever the delta E is positive, when we are minimizing, that is when we are when we have a better move, then we accept that move right away. But in this case, turns out that our move isn't good. So when delta E is not positive, then next thing we do is we calculate probability. In this case, this is E to the power delta E by current temperature. And this probability turns out to be 0.52. Now, next, what we do is, this is a slightly higher probability than 0.5. So we generate, say, a random number, maybe, say somewhere, let's say here, I calculate equals rand, let's say between 1 to, let me do 1000, and then let me divide by 1000 to get a number between 0 and 1. So I get a number, random number 0.89. I want to check what is the probability that this random number is less than the current probability that I have. Actually, given this current probability, 0.52, in other words, we would like to select decide on whether we want to keep the next configuration or not based on this probability. So to actually come up with a concrete decision, what I just did was calculated another random number, one random number between 0 and 1, and I want to check, is this random number less than the current probability? In this case, no. So that means I'm not going to I'm not going to accept the next move. So this means I'm going to change this, delete this configuration, and then throw it away. So I get another random set of numbers. Let me copy it and then paste it again as my next move. Paste the special values only. So now again what I have is a much lower energy, and the probability I get is 0.50. Once again, I calculate the random number. As you can see, it's already 0.2. So is 0.2 less than 0.5? Yes. So even though this probability was 0.5, which is not very high, we are going to select this move because the probability that we got, the random number that we got, is less than 0.5. This means I'm going to accept this move and we are moving forward. Even though this is a bad move, our overall value has increased, we will accept this move. So the next iteration is to generate another random configuration. Here we have -2, 2, and 0. And then copy this value as my next configuration values only. So I get -2 to 0, and then when I look at the overall total score, this is 2.0. And clearly E next is lower than E current. That means I go one row up, look at the delta E, which is simply E current minus E next, and this is positive. So whenever delta E is positive, if we look at the algorithm, when delta E is positive, we accept that move. So since E is positive, this probability, which is 2.2, doesn't make sense, right? But it is not important, because whenever delta E is positive, we ignore the probability value altogether. So even though this number is higher than 1, we can absolutely ignore it. So that means this is our current move, and we accept this move. Now we go to the third iteration. Let's generate another sort of random move from the current configuration. So we take it. So the next current configuration we have is 0, 3, -2. Let me paste this temporarily as the next move. So now in this next move, I see that my E current is 1.23, which is better than 2.0, which was earlier. So my delta E is again positive. So I ignore this very high probability. I mean, this is actually not a probability now because delta E is positive. So I accept this move. That means now we go to iteration 4. We already accepted this new configuration. Let me copy a new random next configuration, copy and paste it as values temporarily. Again, now we look at the total objective function value, 0.67, better than before, of course. So again, my delta E is positive, ignore the probability, and we accept this move. Now iteration 5, I look at this again, take these numbers, generate next set of random values, and then let's see, I consider this as my temporary next setting. So here, this is 1, 4, -2, and then if I go all the way to energy, it has gone up by quite a bit, 1.31. So then I go up here, back again, look at the delta E, negative of course, because the energy is higher. Now I look at the probability. So the probability to accept this minus 0.64 is only 0.2, very low. So let's recalculate our random number, and we get 0.805. So is 0.80 less than 0.2? No. So this means we do not accept this move, and then we delete it, we generate another random move again. So we repeat this until certain iterations, or our energy is quite low, say for example, maybe less than 0.1 or something like that. And then at the end of the day, once this is over, what we want to do is validate this by putting in the values of wx, wy, and wb into the neuron as weights, and make sure that whenever we supply x equals 0 and y equals 0, we get the right output, and so on. So that's how we can trace simulated annealing algorithm. I mean, this is not feasible to actually do it for bigger problems and do it manually. But what this tracing does is helps us understand deep into how the algorithm is calculating delta E, calculating the probability, how the temperature schedule is affecting the probability, and things like that.